Okay, so this is lecture number 1 of Solid Mechanics Learn the Basics in 18 lectures. And today's lecture is all about the two fundamental types of stress, normal and shear stress. All right, so we're going to start our discussion here by looking at a flat metal plate attached to a fixed base. So there we go. We've got the plate there, and we've got the fixed base there. And let's apply a load to the top of our plate. So here's force F. Now, of course, you know that intuitively that because there's a load F applied to the top of that plate, but it's not moving, that force is going to be transmitted through the length of the plate to the base to restrain movement. So we've got internal force that's being carried through the plate and being transmitted to the fixed base here. And what stress is simply a measure of the average internal force within an object at a particular location. So let me write that down. So stress is average internal force within, got ahead of myself there, within an object at a particular location. Okay, so average internal force at a particular location, right? So we could, for example, do something like ask, what is the stress at this location here? Or we could choose, what is the stress at that location there? Or what is the stress at that location there? And to calculate stress at any of those points, let's say point A or point B or point C, since stress is average internal force at a particular location, then calculating the stress at point A, for example, requires knowing the internal forces that exist within the object at location A, or more specifically within the section plane that point A is located in. And similarly, if we wanted the stress at point B, we need the average internal forces, or the internal forces that are located in the section plane of point B. So we've got something like this, where to get stress, we first need to have internal force, which, to get internal forces often requires us to be able to know how to appropriately find support reactions. And to get support reactions, we need to know how to draw free body diagrams. So what we're going to do before we get into the new material here really is we're just going to do a bit of very quick necessary review on support reactions and free body diagrams. Okay, so let's look at support reactions first. Okay, so there's sort of 4 main types of engineering supports we see in this course. We see a roller support that's schematically like this, where we've got a beam, let's say, and a circle below it is signifying like a cylinder, so something the beam can roll on. We also have pin supports. So here's our beam, and this is drawn something like this. So we've got some sort of bracket down at the base here, and then a pin going through the bracket and through the beam there. And then we also see cable or rope supports, and these are schematically represented like this. There we go, make that nice and pretty like that, and then maybe this is at some angle to the horizontal of theta. And finally we have fixed supports. So here we go, and these are schematically represented like that. So to be able to find stress, which requires internal force within an object at a particular location, that often requires support reactions and free body diagrams. So to properly create a free body diagram, you need to know what forces to include for various supports. So let's just quickly go through these. So drawing the free body diagram here for a roller support. Rollers are designed to allow things to roll horizontally. So the roller cannot apply a force in the horizontal direction. It can't apply a force in the direction of that first blue arrow if there's a force being applied like that. The roller would simply roll to the right here because this force can't exist. There's no way for that force to be applied. So what a roller can do, though, is resist a vertical force. So a possible support reaction force here, and the only possible support reaction force is AY here. And I'm assuming here that our point at the roller is labeled point A. So whenever I do support reactions, I always use the labeling system where if a support reaction exists at point A, then I name the force A subscript and then the orientation that that force is in. Okay, now the other thing that a roller can't do is it also can't resist rotations. So if the beam was being lifted up in that direction, then the roller can't do anything to resist that, so it would freely rotate in the counterclockwise direction. So there can be no applied moment at a roller, and this is something that I always see students get wrong. Is people will commonly draw a free body diagram and include a support reaction moment at a roller, and it just can't support that. So don't make that mistake. Okay, so moving on to our pin support here. So pin support, if we took this beam here and pulled it horizontally, the pin would pull back, so we can have a horizontal support reaction force. So again, assuming that this pin is labeled point A, then we can have a force AX being applied at that pin. And if the there we go. If a force that's vertically oriented is being applied, then a downward force will be applied by the pin. So we can have a force AY as well here at the pin, and that can be oriented upwards or downwards. So two support reactions at a pin, AX and AY, and again, no point moment can exist at a pin. All right, cable support. Cables or ropes can only resist tension So there can only be one possible support reaction here, and that is a force that's oriented in the direction of the cable here, and we'll just call that FA for the force that's being applied at our point A there. And because the tension has to be parallel to the length of the cable, then if this angle here originally is theta, then this angle is also theta over there. Now, a fixed support, here we go. When I'm in class, I always have a metal ruler with me, and I'm holding one end of this to sort of demonstrate a fixed support. And you can sort of imagine that if this is a ruler and that fixed support is my hand holding it, then if I pull down on that ruler, then my hand is going to push back upwards. So there can be a fixed support that is in the vertical direction. We'll call this AY. And if I took the ruler and pulled it to the right, my hand would pull back to the left. So there can be a horizontal support reaction, AX. And then there can also be a point moment in this case. So again, these are assuming that that's point A there. And we can have a moment at the wall, M subscript A, for the moment about point A. Okay, so that's support reactions, quick review of support reactions there. So now we need to go to looking at free body diagrams. So free body diagrams. So let's take a really simple example for this and just look at a beam here that's being loaded, and let's say that that's a roller on that side and that's a pin on that side, and maybe we have one force F1 that's oriented like that and another force F2 that's like that. So the question is what goes into a free body diagram? Okay, when you draw a free body diagram, you're basically taking away everything that touches the object that you're drawing the free body diagram of, and then including any forces that are applied by those things that were touching the object, as well as other forces, like forces that are inherent to the object itself or forces that are being externally applied to it. So there's three main categories of forces that get included in a free body diagram. So first of all, we've got any externally applied loads. So in that case, that would be the loads F1 and F2 here. So that's the external loads. Okay. Number two, support reactions, because when you draw a free body diagram, you're taking away the supports. So in their place, you have to put the forces that those supports would have been applying to your object. So support reactions. Okay. And number three are forces that are inherent to the object itself, and we call those body forces. So those are things like the weight of the object. Okay, so looking at our beam here, if we're drawing the free body diagram of this, then we've got just the beam itself, right? So we're taking away the supports here. So the first thing we include are the externally applied loads. So we've got our load F1 and our load F2 there, and then we've got our support reactions. And always when you're doing this, if you doing a problem and it hasn't been labeled appropriately, then it's always a good idea to label points when you're starting. So we've got, let's call that point A there, and this point B over here. So here we've got A, and here, well, not there. Here we've got point B. Okay, and by putting on those labels, that allows us to label our forces appropriately and then stay organized when we start using variables and equations. Okay, so we've got a roller support at A, so we know we can only have a vertical support reaction, so this is A subscript Y, and B is a pin support, or there's a pin support at B, so we have B subscript Y, and then we can also have B subscript X in this case. So we've taken care of our external loads, taken care of our support reactions, so now we need to deal with the body forces. And the body forces are, in this case, simply the weight of that beam. So that's going to be located right at the center, at the beam's center of gravity here, and we'll just label this W. Now, in most of the problems that we're going to do, the weight of the object itself will end up being negligible in comparison to the externally applied loads. And that's just simply a function of common engineering materials being significantly stronger and having the ability to bear significantly more load than the loads caused by their own weights. So there'll be some problems where we have to include the weight of the object itself. There will be other problems where you won't have to. It will be pretty obvious for the problems in this course when you do have to include the weight of the object itself and when you don't. For example, if I give you a problem and I specifically tell you what the density of the material is, then it's a good indication that you need to include the weight of the object. Conversely, if I give you a problem and I don't mention anything about the density of the material or what the material is, it's a pretty good indication that the weight is negligible. In practice, if you are ever unsure whether or not the weight of a structure or object will be negligible, then you always include it. And if it does turn out to be negligible, or calculations or estimates show that it can be neglected, then at that time you can neglect it. But whenever there's a doubt, include. Okay, so that's how you draw free body diagrams. So just going back here, so we said what we're really interested in is calculating stress, but we needed to get stress, we needed internal force, and internal force requires support reactions to enable us to draw free body diagrams. Okay. So actually it's sort of more here the other order that things come in. Just delete that here. We actually sort of, to get internal force, we need a free body diagram, and to get a proper free body diagram, we need our support reactions. Okay, there we go. So now your notes or my notes or the notes that you're getting from me are nice. So good, we've got that all there. So now that we've taken care of support reactions and free body diagrams, now we can start looking at the new piece, which is in internal forces, and then how to use those to calculate stress. So we're just going to keep chugging along with that same example we were sort of looking at there before with the flat plate on the fixed base, and we'll attach some numbers to it now, maybe, or maybe we'll start without numbers, and then we'll throw the numbers in a minute. So let's just draw that plate again here. Okay, so we had our plate, here's our fixed base, and here's our load being applied, and we'll just call that F now. So let's say that we wanted the stress in this object at some location C. So stress at C is our question mark. That's our question. So to get the stress at point C, what we need, well, stress is average internal force at a location. So if we want the stress at C, the first thing we need are the internal forces at C. And the way that you get internal forces is by pretending to cut the object through point C and then analyzing the free body diagram of one side of the object or the other. Okay, so what we're going to do here is at point C, we're going to pretend that we cut the object in half at that location. And then we're going to look at drawing the free body diagram just of that top portion here. So the top portion here looks like this, where we've got our load F here. And then what we've done is we've cut right through a solid object. So in our free body diagram here now, we need to think about what we need to include. So we've included the externally applied loads. Because we've cut a piece of material in two, the forces that show up at that cut junction are just like the forces that are existing at a fixed support. So we can have a vertical force, a horizontal force, and a point moment all at location C here in the plane of point C. And because these are internal forces rather than support reactions, they get special names here. So first of all, this force right here, that is a normal force. And we'd give it the notation N subscript C for the normal force that exists at point C. Now, I am just going to clean this up a bit because I don't like the way this is looking here with that call out right there. So let's erase that and let's put those forces back in here. So this is our normal force at location C, and then I'm going to put on that horizontal force, and then I'm just going to drop the moment down here. Okay, so this is a normal force. So normal force, there we go, normal force NC. So normal forces are internal forces that are defined by being oriented perpendicular to the section plane or section cut that's being made. So this is a normal force. So it's a normal force because it is perpendicular to our section cut that we've taken. Okay, And then the force in the horizontal direction here is called a shear force, and we give that the symbol V and V subscript C to denote that it's the shear force at location C. So shear force VC. And what makes it a shear, an internal shear force, is the fact that that force is oriented parallel to the section cut that we've taken. So shear force, because it's parallel to our section cut. Okay. And MC is the internal moment at location C. So we'll just have that in, oops, be helpful if I could spell that correctly. Internal moment at C. Okay, there we go. So the internal forces when we're drawing free body diagrams and we've taken a section cut, there's sort of like support reactions. So we've got our externally applied loads, which was load F, our internal forces that are like the support reaction forces after we've broken this object in two, and then we've got our body forces. So this whole object here is going to have some weight, and the weight would be located at its centroid there, so that would be W. And if, let's say, this is point A up here and this is point B down there, then this would be the weight of the whole object, WAB. When we're including the body forces for the small portion of the object that's resulted from us taking the section cut through it, right now we just have the portion AC here. The weight that's included is only the weight of that section that we've drawn. So this is WAC, which is going to be smaller than WAB, right? So you only include the forces that either act on or are inherently part of the portion of the object that you've chosen to draw. Okay, so now we've got internal forces. So we're working our way backwards. So we've got internal forces. So now we can talk about stresses. So let's just see if we can take this guy here. Okay, we'll just copy that and we'll just bring him over to a new page here. Okay, paste that there. Okay, good. All right. So stress, to remind you, stress is average internal force at location. Okay. So we've got three internal forces: normal force, shear force, and an internal moment. Now, in today's lecture, we're going to be dealing with the stress that's caused by the internal normal force and the internal shear force. Stresses that are caused by internal moments we're not going to deal with for a little bit. That's not going to come up until, let me just see here, bending stress lecture 9. Okay, so you don't need to worry about that at this point. You should still obviously be able to calculate internal moments, but you don't need to know how to calculate the stress that results from them. All right, so we've got a normal force NC. Normal forces cause normal stresses. Okay, so that's going to create a normal stress. and we give normal stresses the symbol Greek letter sigma, lowercase sigma. Okay, and normal stresses resulting from normal forces are really easy to calculate. All you do is to calculate normal stress, you take your internal normal force and you divide it by the area that it's acting over, right, which is the cross-sectional area. So we've got n divided by a, sigma equals n divided by a, there. So it's probably worth taking a moment just to talk about units at this point. So let's do that. So units. So in this course, we're going to be dealing with both international units, so SI units, and we're also going to be dealing with US units. So we've got forces in SI that are going to be measured in newtons, distances measured in meters, and stresses. If you look here, we've got force divided by cross-sectional area, so that's newtons per meter squared. That's a Pascal. So stresses are in pascals, and often we'll, instead of newtons, be dealing with kilonewtons, and instead of pascals, we'll be dealing with kilopascals, or more often megapascals. So here we've got 10 to the 3 pascals and 10 to the 6 pascals. Okay. Now we'll also be dealing with US units. So in US units, we've got force in pounds, and it doesn't matter if it's pound mass or pound force, because it's a one-to-one conversion between pound mass and pound force. So you don't need to be concerned about whether something has the notation LB subscript M or LB subscript F, because 1 pound mass is 1 pound force. So it's easy. We'll also be seeing units of kip. And kip is simply a kilopound. So this is 10 to the 3 pounds. Okay. Lengths in US units will be dealing with inches. And of course, there's feet as well, where we've got 1 foot is 12 inches. So we'll see lots of dimensions given in feet. And then in terms of stress, where we've got force divided by area, right? Here we measure stress in pounds per inch squared. Pounds per inch squared, that's PSI, pounds per square inch. Okay. And we'll also be seeing stress in KSI, which is simply kilopounds per square inch. So that is 10 to the 3 PSI. Okay, so we've taken care of the basics of our units there, and we've got normal stress. So just like normal stress, an internal normal force produces normal stress, and internal shear force produces shear stress. So we've got shear force V would produce shear stress, and we give shear stress the Greek letter tau. Okay, so there's my tau. Now let me go back here again and just grab our little drawing here. Okay. cut. Actually, no, let's not do that. I didn't want to cut it out there. I just wanted to copy it. It's probably already on the clipboard anyway, but can't remember these things. So here we go. Let's paste it there. Okay, good. So shear force V. So to get shear stress, we do exactly the same thing as we did for normal stress. Our equation for shear stress is actually called average shear stress to help identify it separately from transverse shear stress, which we'll get into later. We simply take the value of the internal shear force and again divide that by the cross-sectional area to give a measure of the average internal force per unit area, and that's shear stress. So we have tau equals V divided by A. Okay. So there we go. There are equations for normal stress and shear stress. Now, it's important to realize that normal and shear stress do fundamentally different things, or they're fundamentally different from one another. So if we look at the effect of that internal normal force on the cross section that we've drawn, so let's just draw that there, right? And we've got this force that's oriented this way. That force is pressing in on the material, causing it to become just a little bit shorter. So it's moving it upwards by that amount. So if you were to look in sort of on an atomic level here, you've got atoms in the metal that are like this, and they are being squeezed closer together than they naturally want to be. So they're resisting that compression. And normal stresses that result from normal forces are always related to atoms or material being either compressed together more than they naturally want to be, or pulled apart from one another more than they naturally want to be separated. And the pulling apart is called tensile stress, and the pushing together is called compressive stress. So that's normal stresses. So this one here, this normal force, let's do that in blue, normal force, that goes to create a compressive normal stress, right? So normal stress, sigma, always compressive or tensile, right? So pushing together or pulling apart. Shear stresses, on the other hand, shear stresses are a bit different. So if we look at the effect of our internal shear force here, V subscript C, put that back here, good. There we go. Let's just grab V subscript C here. The action of VC within this material on this sort of atomic level is there are atoms within this metal, and VC isn't acting to move those atoms farther apart in that direction. What it's really doing is shifting one row of atoms relative to the other. So, it's taking these guys and moving them to the side, displacing them to the side relative to the ones above. So it's really sort of a shearing or a skewing action that internal shear forces have. So they're quite different to the effect of an internal normal force. So shear stresses are fundamentally different than normal stresses, and shear stresses aren't tensile or compressive in nature. They're just shear stresses. So shear stresses, not tensile, they're not compressive. Shear is just shear. Okay, that's good. So let's go back and we'll take that little example problem that we've done, and we'll just stick some numbers to it. And engineers like calculations, so we'll humor you and put in some numbers and calculate what those stresses actually are. So let's just grab this back here, and we'll use that. Okay, so paste that into place. There we go. Perfect. And we'll just do some erasing here. Okay. That's not even a nice drawing. Don't know why I bothered with that, but okay. Let's just start entirely again. Here we go. Let's scratch that. Okay. Start from the beginning and make it a little bit nicer. Okay, so we've got our flat plate here. It's looking a little bit wider than it looked at last time. It's okay. And let's say our force is like this. And let's say our force is an 8 kip force. So that's 8 kilopounds, 8,000 pounds. And maybe it's oriented at an angle. Let's keep things simple. Let's go 30 degrees here, and let's use that same point we were using previously, point C here, and throw some dimensions on. Let's say that this is 1 inch, and then the total length of this object is 4 inches here. And what we want to know is the stress at C if the plate is 2 inches by 2 inches in cross section, and it is made of, let's say, aluminum with a specific weight of 0.1 pounds per cubic inch, question mark. So stress at C if the plate's 2 inches by 2 inches in cross section and is made of aluminum with a specific weight of 0.1 pounds per inch cubed. Okay, so again, if we want the stress at point C, what we need are first the internal forces at point C. That requires doing a section cut at point C and drawing the free body diagram of one side or the other. So take a section cut through point C there, and then let's draw the free body diagram just down here. So there we go. Okay, and we've got here's our 8 kip there. Okay, so let's put on our forces. So we've got our internal forces. Of course, we can see that our normal force is going to have to be acting downwards for some of the forces in the y direction to be 0. So this is n subscript c. Our shear force is going to need to be acting this way, v subscript c, to balance the horizontal component. And our internal moment is going to need to be acting around in this direction here. It's no problem if you don't get the direction of those internal forces on properly when you initially draw your free body diagram, because when you do your equations of statics, if you've got one of those arrows in the wrong direction and you go through the math properly and get a negative number, that just tells you that your arrow was in the wrong direction or your assumption was wrong. And what's really important in this course to do is, if that's the case, you just change your numerical value that you end up with to a positive value and then change the direction of your arrow. And that's going to be important for determining whether stresses are compressive or tensile, for example, and then particularly later when we get into combined loading, and we're adding normal stresses that have been caused by different internal forces together. It's really important that you have your arrows in the right direction so that you don't get confused. Okay. So we've got our externally applied load, we've got our internal forces, now we need the body forces. So remember, this is just the weight of this little 1-inch segment. So this is going to be WAC. Okay, so all of the problems that we encounter in this course are going to be statics problems. So for statics, you've got some of the forces in the x direction has to be 0, and the y direction has to be 0. Some of the moments has to be 0, and that's for two-dimensional. And then when we get into three-dimensional problems, we end up with 6 equations of statics, forces in all 3 directions, and then some of the moments and some of the torques if there's torques involved. Okay, so here the first thing that's sensible to do is calculate the weight WAC. So we've got WAC is going to be equal to what? It's going to be equal to the volume of segment A. Well, that's not a great thing to write because it's the same symbol as internal shear force, so we'll erase that. So we'll just say volume of segment AC multiplied by the specific weight. So that is 2 inches by 2 inches by 1 inch for the volume, and then the specific weight is 0.1 pounds per inch cubed, so that's giving us 0.4 pounds. Now I'm not going to show units in my equations. When I write them out, I find that units add too many extra characters to equations, and I tend to end up making more mistakes when I punch things into my calculator if I've got units included there than if I don't. But if you're ever not sure about what the unit on the back end of an equation is actually coming out to, then I suggest that you just do a simple unit check, and that involves writing in the units on a new line and just including the units for everything. So that would look something like inches multiplied by inches multiplied by inches multiplied by pounds per inch cubed, and then you can see that inches cancel out and we get pounds out the back end there. Now when you're doing problems in US units, what you want is you want to have everything in your equation in units of pound, inches, psi, right? So if you're doing a calculation and you're looking for stress, if you put your inputs in pound and inches, then you'll get psi out, and then you can convert it to ksi as appropriate. Or if you're looking for a force and you've got stress and dimensions, then if you use psi in inches, you know you're going to get pounds out, etc. So use pound, inches, psi. If you're dealing with SI, use newtons, meters, pascals. Okay. But of course, that's not the case for this particular problem here, so we don't need to worry about that. Okay. So 0.4 pounds, right? Not much weight was the actual weight of the object. So now let's actually apply our equations of statics. So I always kind of like to formally do these. So we're going to do sum of the forces in the y equals 0, and we're going to take our upwards direction to be positive. And it doesn't matter if you take upwards to be positive or downwards to be positive. You just have to make it consistent in terms of the arrows that you've drawn on your diagram for this one equation. So let's see what we've got here. We've got 8,000, right? So I'm changing that 8 kip here into pounds. 8,000 times the cosine of 30 degrees, so that's upwards, so it's positive. And then we're subtracting the weight WAC that's acting downwards, right? So we've got minus 0.4 here, and then we're subtracting our normal force NC, and we're saying that all has to equal 0. So do the math on that. NC is equal to, when I ran it through my calculator, I got 6,928 pounds, right? Which is 6.9 KIP. Now, if you look at the magnitude of this load in relation to our weight of the object, right, you'll see that we've got, 6,900 pounds versus 0.4 pounds. So in this case, the weight of the object itself in relation to the externally applied load in creating the normal forces is totally negligible. So we can neglect that entirely. And in fact, it doesn't even show up in that 6.9 when it's rounded, of course. So you look at more of that at this stage right here. When you had the 0.4, you'd actually compare it to the externally applied load and say, well, 0.4 compared to 8,000 doesn't matter. So then you wouldn't include WAC in that equation at all. So we can just remove it from there. Okay, so we've got our normal force NC. Let's go ahead and calculate what our normal stress is then. So we've got the normal stress at point C is going to be the normal force at C divided by the cross-sectional area at location C. So we've got, let's see, 6,928 divided by 2 inches by 2 inches, and then we've got pounds divided by inches squared, so we're coming out with PSI when we make that calculation. So that gives us 1,732 PSI, which is equal to 1.7 KSI. Okay, there we go. And it's always nice to put your answers in a box with an arrow clearly indicating them. The neater you can be in general, the better, the more organized you can be, the better, because as engineers, we're always having people double checking our work, fellow engineers, to make sure that, simple mistakes like numeration errors haven't been made. So the neater that you can make your work in general, the more time that you're going to save the reviewer, and time is money. So it's good to make things neat. Okay. So we've got the stress now. If we look at that stress, the normal stress at location C, we can see that the normal force at location C down there is that's pulling away from the rest of the object. So that normal force is taking the material at the location of the section cut and pulling it down. So that is a tensile stress. And when you're thinking about whether stresses are tensile or compressive, always look at the direction of the internal normal force. And if it's pulling away from the rest of the material that you've drawn, then it's a tensile stress that's being created. And if it's pushing into the rest of the material, then it's a compressive stress. So that's a tensile normal stress. So we can just write below that in brackets, tensile. Okay, there we go. So now let's return and get our internal shear force, VC there. So to get that, we do sum of the forces in the x direction has to be equal to 0, positive direction that way. And then it's always nice to have things on the page that you're working here. So we'll just grab that quickly, copy that, go back over to our page, paste that there. There we go. Okay, a little bit of erasing up top, and we're set to go here. So, okay, so for our equation, we've got 8,000, right, multiplied by the sine of 30 in this case, and that's acting towards the left, so that's a negative in terms of the sign convention that I've set up. And then we've got plus VC is equal to 0. So VC is, of course, sine of 30 is a half, so this is 4,000 pounds. And then the shear stress at location C will simply be equal to the internal shear force at that location divided by the cross-sectional area at that location. So you've got 4,000 pounds divided by cross-sectional area, 2 inches by 2 inches, gives us what? It gives us one, yeah, of course. Here I am looking at my cheat sheet over here of pre-calculated numbers. Sometimes you should just, do the math in your head, of course. So we've got 1 KSI. There we go. And of course that's neither tensile nor compressive because shear stresses are not tensile or compressive. So there's an example for how to calculate stress at a point. Now, if you notice, if we go back to the start here with this example, I never did calculate the support reactions in this example before we took our section cut and found the internal forces. And in certain problems, you won't have to do that. You'll be able to calculate your internal forces right away without having to find your support reactions. In other problems, that's not going to be possible to do, and you'll actually have to calculate support reactions first before you make a section cut and analyze one side or the other side of the object. So let's, well, I like doing examples because examples are valuable for learning. So let's do one more example, this time with a problem where you need to find support reactions first. So here we go. Example. So this example is kind of like, the structural support for an awning over the entrance of a building, for example. Awning over the entrance of a building could be supported by, a beam that looks something like this, where you've got a horizontal beam. It's, let's say, pinned to a wall here. Okay, and then supporting it on the other side is a cable that goes up and connects to the wall here. That's kind of a sloppy hatching job there. Not that it matters, but we'll clean it up just because we can. There we go. And let's put in some dimensions here. So let's say that this overall length is, let's do a metric one here, 2 meters. And let's say that this angle is 60 degrees down here, which makes the other angle 30, of course. And now let's stick in our loads. So we've got, let's say, you know, something like snow loading, for example, a linearly distributed load maybe. So here we go. We've got a load distributed all the way along, and of course that's not really drawn properly. That should be on the top of that beam. So let's try that again. There we go. So there we go. So acting all along the top of that beam, and the value of that will be 2 kilonewtons per meter. So for every meter length of beam, there's 2 kilonewtons of weight sitting on top of that. And then let's say that we've also got the beam's cross section. Wow, that was a terrible attempt at that. Sometimes, you know, writing on a screen with a stylus just gets the best of you, or at least I can try and blame it on that. So cross section of beam. So let's say it's something like a hollow steel section, and it's a hollow rectangle like this, and let's give it an odor dimension here of 100 millimeters, and let's give it an inner dimension here of 90 millimeters. So the wall thickness on each side is 5 millimeters. And then here we'll say that the inner dimension is 50 millimeters, and then the outer dimension here is 60 millimeters. Not the most beautiful dimensioning, but it'll do. Okay, so the question that we want to ask is, let's say we are interested in knowing what the stress is at location C in this beam, and C is there on the longitudinal, or on the the horizontal view, and on our cross section it's located there. All right, and let's put in some other points. So that pinpoint is point A, this pinpoint is point B, and the question is stress at point C is the question. Okay. All right, and we'll leave it so that we're not told anything about the material of that beam, and because we're not told anything about the material, we'll assume that the weight is negligible. So maybe we'll just start our next page with that first line. So assuming that weight is negligible, right? Now, let's take this. Let's try that again. Let's take this right here and copy it over into our next page. So copy. Okay, and let's put it right there. Perfect. Okay. So if we want the stresses at location C, we need to take a section cut through C to find the internal forces. So let's just try doing that right away, right? So if we take a section cut through point C and draw the free body diagram of one half of the object or the other half to reveal those internal forces, you always get the same answer for internal forces if you do one half of the object versus the other half. I always like to do, the side that I think is going to be easier based on the number of forces involved. So let's do the left-hand side here. So we've got, there's our section cut. Now, what do we include for forces here? We include the externally applied loads, so that's only the portion of the distributed load that is sitting on top of that little segment of beam, and we didn't actually define where that was. So I'm going to go back here and say that this is, no, let's not make it 1. That's too round of a number. So let's say that that's 0.5 meters there, where location C actually is. Okay, so this is just the portion of the distributed load that is sitting on top of the beam, 2 kilonewtons per meter, where we've got location C right there. And so that's our externally applied loads, and now we have our support reaction forces, so we know we can have a vertical support AY and a horizontal one AX, and then we've got our internal forces, right, which also sort of are included in the support reactions because we've cut through something solid, so we can have a normal force at location C, a shear force at C, and an internal moment M subscript C are all possible. So you can always have those 3 when you cut through something solid. Now, we've got, a whole bunch of variables and more unknowns than knowns. So for example, some of the forces in the y direction, we're going to have unknowns of AY in that equation and VC in that equation. One equation, 2 unknowns, we can't solve that. Some of the moments about point C, if we tried that, we'd have MC involved in that equation, and AY again, so we can't solve that. So when you do something like this and you try and directly take a section cut and solve for your internal forces and you can't, then you have to take a step backwards and find support reactions first. Okay, so can't find internal forces. Let's try that again. Can't find internal forces. So what are we going to do? We're going to analyze the free body diagram of the whole object and find support reactions first. Okay, find support reactions first. Okay, cool. So let's do that then. So let's go to a new page here, paste that back on. There we go. Perfect. To find support reactions, right, we want to take this and modify it to be a free body diagram. So we're going to take out the support here at A and replace that by just the point. There we go. Fix that up. There, perfect. And then we're going to take out our cable. Okay, here we go. Take that out. And we're going to replace that by the appropriate forces. So we'll do that in a second, just after we fix up these other loads that we messed up here. Okay, great. Okay, so our force at point B, right, that's a cable support, so we have one force that is called, I'll just call it FB for the force that's applied at point B, and we know the angle of that's 30 degrees to the horizontal there, and then we've got our force at point A. So we can have a vertical force, that's AY, and a horizontal force, and that's a subscript X there. And then body force of the object, well, we said we didn't know what material it was, so we're assuming the weight's negligible, so we don't need to worry about that. Okay, so we've got our drawing here, and now we're going to find the support reactions. So if we do some of the forces in the y direction, we're going to have 2 unknowns, so that doesn't make sense. And then some of the forces in the x direction, 2 unknowns, so it doesn't make sense. So what does make sense is to do some of the moments about point A. So then AX and AY both cancel off in that equation because they've got 0 moment arm there. So we'll do some of the moments about not point A here, not point C, but point A. is equal to 0, and we'll take the counterclockwise direction as negative. Again, it doesn't matter whether you choose to take clockwise or counterclockwise as being positive for equations of statics, just as long as you're consistent for the equation that you're dealing with. Okay, so some of the forces, some of the moments about point A is equal to 0. So in the positive direction, for what I'm taking to be positive moments, we've got the moment that is caused by the vertical component of FB here. So the vertical component of FB is FB multiplied by the sine of 30, and the moment arm is 2 meters. And that is counterbalanced by the moment caused by the distributed load. So the distributed load, we want to deal with that by finding its resultant, and then the magnitude of the resultant, and then the distance that that resultant is away from point A. So the magnitude of the resultant is 2 kilonewtons per meter multiplied by 2 meters, and then it's going to be located right in the center for the resultant, so that's 1 meter. And then that's all equal to 0 there. So coming out of that equation, we've got FB is equal to 4,000 newtons. So now we can do some of the forces in the y direction is equal to 0. So some of the forces in the y direction is equal to 0, with positive being upwards. So now in the upwards direction, we've got our unknown AY plus the vertical component of FB, which is 4,000, the value of FB sine 30 degrees to get the vertical component, minus the value of our distributed load. So we've got 2,000 multiplied by 2. That all has to be equal to 0. So we've got AY is 2,000 newtons now. Okay, now we can do some of the forces in the x direction is equal to 0. We'll take it over to the right as positive. So negative direction, we've got FB, or the horizontal component of FB. So we've got minus 4,000 multiplied by the cosine of 30. And plus AX, that's the only other horizontal one, equals 0, and then that gives us AX equals 3,464 newtons. All right, perfect. So we've got our support reaction loads now. And what I'm going to do is I'm just going to write them in on this page while I can see them. So this is 3,464. And this is 2,000, and we've got this is 4,000 up there. Okay, and now I'm going to grab this here, and we'll copy that, and we'll move that to a new page. Okay, so we have it ready there. Okay, perfect. So now we're in a position where we can take our section cut through point C and analyze the free body diagram to figure out what the internal forces are. So there's our section cut through point C, and we'll do the left-hand side of that. So I'll draw it over here. Okay, there's our section cut. So externally applied loads. So we've got just a bit of our distributed load. Okay, so this is 2 kilonewtons per meter. Okay, and just to remind ourselves, this distance here from A to C is 0.5 meter. Okay, we've got our support reactions at point A. So we've got here AX, and that is 3,464 newtons, and then we've got AY. Y is 2,000 newtons, okay. And then we've got our internal forces, because no body force here. So let's put our internal forces on. So we've got, and I'm not going to pay attention to which direction I'm doing these in right now. I'm just going to put them on in an assumed direction and then let the math take care of itself. So we've got shear force VC because that's a force parallel to the cross section or the section cut that I've drawn. The plane of the section cut, we've got normal force NC, and then we've got our moment M about point C, and here's our point C right there. Okay. So, some of the forces in the X is trivial, right? Equals 0, and we've got NC is equal to AX is equal to 3,464 newtons, right? And we redrew NC in the right direction because it's counteracting AX. So let's go ahead and get our shear force, VC, so we can do sum of the forces in the y direction equals 0, upwards is positive. Okay, so what have we got here? We've got our support reaction AY, so that's positive 2,000. And then we've got the resultant of the distributed load that's being applied to only our 0.5 meter length of beam. So that's downward, so it's minus 2,000 and then multiplied by the length to get the resultant. So there's minus 0.5, and then we've drawn our shear forces upwards, so that goes as positive VC, and then that's all that we have. So that equals 0 there. So coming out of that equation here, we've got VC is equal to minus 1,000. Okay, minus 1,000 newtons. Okay, so that 1,000 minus 1,000, the negative sign indicates that we drew VC with the assumed wrong direction. So that's fine. The important thing to do is change this to a positive value now and go over to your diagram, scratch out VC or the arrow that shows VC and put it in the right direction. Remember, you always want your arrows being in the correct direction because that's really going to help when it comes down to calculating stresses later on. All right. So now that we've got our internal forces, now we can actually calculate stresses. So the normal stress, let's get black there. The normal stress at location C is going to be, let's use actually the right symbol for stress, sigma subscript C. The normal stress at C is the internal normal force at C divided by the cross-sectional area at C. So here we've got 3,464 newtons divided by, then let's just go back and look at our original drawing. So we want only the cross-sectional area, so we're taking outside dimensions minus inside dimensions. So that's 100 millimeters by 60 minus 90 by 50. Okay, so we'll change everything to meters because remember newtons meters will give us pascals. So we've got 100 millimeters, 0.1 multiplied by 60, 0.06 minus 0.09, 90 millimeters, and 0.05, 50 millimeters. And that is going to give us, when you do the number crunching, 2.3 times 10 to the 6 pascals, which is 2.3 megapascals. Okay, megapascals, best unit for the answer. Always nice to give answers in the best possible unit, and that's megapascals for this answer. All right, and then is that tensile or compressive? Well, again, look up at the little free body diagram that we drew and see the direction of NC relative to the section cut that we drew. So NC is pushing in on the section cut, right? So that's compressing this portion of the beam that we've drawn. So that's a compressive normal stress. So we can write under that it's, and just make a notation there that it's compressive. Okay. Now I think we can fit this in on the same page. We've got tau at point C, so the shear stress at point C is the internal shear force divided by the cross-sectional area at that location. Tau C equals VC divided by AC. Kind of looks like an E there. Let's clean that up. There we go. And what we have for numbers in that is 1,000 divided by 100 mils by 60 mils minus 90 and 50. Okay, and that's going to give us 666 times 10 to the 3 pascals, which is 666 kilopascals, kPa. We'll do our box with our arrow. Okay, so that brings us to the end of that example. So and the end of the lecture. So now you know what normal stress and shear stress are and how to calculate them. Remember that stresses only make sense when you're talking about the stress at a particular point, and if you want the stress at a particular point, you first need the internal force at that location. And to get the internal force at that location, all you do is cut through your object and analyze the free body diagram of one portion or the other portion to get those internal forces. Okay, so I'll see you again for lecture 2.